Hess's law doesn't just work for problems involving enthalpy changes of formation. You can combine any enthalpy changes so long as you have a valid reaction sequence. One of the other types of data which are used really commonly are enthalpy changes of combustion, which remember is written like that for short, delta CH. It's the enthalpy change of combustion, which is, if you just want to remind yourself of the definition, is the delta H when 1 mole of the compound burns completely in oxygen, is what delta H of combustion is. And burns completely, remember, means burns to form carbon dioxide and water. So those have been measured for lots and lots of organic compounds. So again, they're data that are quite widely available, and you can use them in Hess's law cycles. So let's look at an example where we can do that. So here's a reaction that you know about. If you have an alkene, you can react it with hydrogen. You need a nickel catalyst, but that's not involved in the overall equation, so it's necessary for the reaction, but it's not actually going to affect the delta H. So alkene plus hydrogen will give you an alkane. So here you've got buta-1,3-diene, so 2 alkene groups reacting therefore with 2 moles of hydrogen to give you butane. And the data we've got to play with in order to work out this number, so this is what we're trying to find, is delta H of reaction here for this process. And the numbers we've got to play with are not enthalpies of formation, they're enthalpy changes of combustion. So again, we're going to combine them by having a 2-stage pathway like this, but what goes in the middle is not going to be elements this time, because when combustion happens you don't get the elements. What happens when you burn these compounds is that you form carbon dioxide and water. So we could balance that up and work out how many carbon dioxides and how many waters you would get. But just as we did with the formation ones, where we decided it wasn't worth actually working out the formulae of all of the elements and how many moles of each you would need, we just wrote the word elements. We can do the same here. And we can say, right, when these various substances burn, what you get are the combustion products. And you could just write that, or you could write that CO2 and water. But we're not going to try and balance it up, because it's just kind of a waste of time. Unless it asks you to do that, then it just comes out in the wash, and you don't need to worry about it. So we're just going to write combustion products at the bottom. So let's feed these numbers in. So again, the crucial thing is you've got to get the arrows pointing in the right direction, and you do that by remembering what combustion is. So you take a compound like this, or this, or this, and you burn them and they turn into the combustion product, and that tells you which way the arrow goes. This burns and turns into that, so the arrow goes that way. Butane burns and turns into the combustion products, so the arrows go that way. Okay, so those arrows are going a different way than the data arrows went in the formation cycle, but don't just sort of memorize that as some random rule. Just think about what the definitions are, and then it's obvious which way the arrows go. So we can put the data on there now. We've got 1 mole of butadiene, so that's minus 2540. And we've got 2 moles of hydrogen, so that's minus 286 times 2. Okay, so if we add that lot up for those 2 substances burning, we get minus 3112 kilojoules per mole. Okay, so very exothermic, negative number, which is what you'd expect for a burning reaction. On the other hand, if we take 1 mole of butane and burn it, delta H is minus 2878, going that way. So what we then have to do is to invoke Hess's law and say what we're interested in is this delta H across the top here, delta H of reaction, and we're going to break it down into 2 legs, same as we've done with delta H of formation. And again, you get the delta H's for each of these legs by comparing them with the data arrows that you've got. So going down here is -3112, and this is exactly the same thing. Okay, the arrow's going in the same direction, so it's just the same number, same sign. But the second leg of our journey, from left to right, goes up here, and you can see that's the opposite of that one. So instead of burning butane to make carbon dioxide and water, we're unburning carbon dioxide and water and turning it into butane. So because we're changing the direction of the arrow, we change the sign, and we get +2878. And we can then just combine those numbers. So we get delta H of reaction is equal to -3112 +2878, which is -234 kilojoules per mole. Okay, so it's exactly the same kind of logic, but because we're using different data, you just have to be very careful and recognise that it's a different looking cycle. It doesn't have elements at the bottom because those were not enthalpy changes of formation. Because they're combustion data, you put the combustion products at the bottom and you make sure the arrows go in the right direction. But if you just tell yourself, what is combustion? It's when you burn something and it turns into the combustion products. That tells you which way the arrows go. And the rest of it then just follows fairly straightforwardly from that. One thing you perhaps have picked up on is that I've been a bit cavalier here with the fact that a combustion reaction involves these things reacting with oxygen, and I haven't explicitly mentioned the oxygens at all in doing any of the calculations. And that's actually fine, but I think it's probably important that you realise that I'm not cheating in doing that's a legitimate thing to do. So let's just go through that a little bit more carefully, just so that you won't worry about it, but hopefully at the end you'll conclude, yeah, that's fine, you can just ignore them. So if we write in the molecular formulae here, we've got C4H6 and C4H10, and so we can work out, therefore, that the combustion products, if we write them in explicitly, are going to be 4 CO2s from the 4 carbons, and then we've got 6 hydrogens here plus another 4 makes 10, so 10 hydrogens altogether, so that's 5 H2O. So those will be the combustion products. And of course, because we've got 4 carbons and 10 hydrogens here as well, then it's going to be the same, obviously. So what does that mean? Well, that means that we actually need 4 2s are 8, plus 5 is 13 oxygen atoms. 13 oxygen atoms being fed in there. So that means in the combustion reaction, 13 oxygen atoms is 6.5 O2 needs to go in there, okay, to make that combustion reaction possible. And of course, the same 6.5 O2 go in here as well. But you can see that when we combine the two reactions together, so the orange route, which goes down here and up there, and therefore corresponds to the overall reaction, we're taking in 6.5 O2s there, but because we've now changed the direction, we're giving the 6.5 O2s back out again. So they're used up, and then they're regenerated, and therefore they make no overall contribution to the delta H, and that's why we can get away with ignoring them. So you have to be careful with that in enthalpy cycles. It doesn't always work out quite as simply as that, but in combustion cycles it does. So if you're using enthalpy changes of combustion, you can confidently just not bother mentioning the oxygens. So it would be fine if it really bothers you, you could do it like that, put the oxygens in to balance everything up, but it won't make any difference to the numbers you get, and therefore it's easier actually in practice just to say, well, I understand that the oxygens I take in here are regenerated there, so there's no point putting them into the cycle, and the number is exactly what you thought it would be, not having thought about the oxygens at all. So here's another example using enthalpy changes of combustions. This time we get this slightly weird looking compound. This is called epoxy ethane. So you get this 2 carbons, 2 CH2s with a bridging oxygen like that, which reacts very readily with water to form this compound, which is called ethane 1,2-diol, which lots of you are familiar with. That's the main constituent of antifreeze in cars. So again, this is one of those where they tell us what the overall enthalpy change of reaction is, so minus 115 kilojoules per mole, and they also give us the enthalpy change of combustion for this product, but not that one. Okay, so the job here is going to be to find the enthalpy change of combustion for epoxy ethane. So as soon as you see that the data you're using are combustion data, that's the crucial thing. You look at the data that you're going to be using in the calculation. If they're formation data, you do a cycle involving elements, but they're not. They're combustion data, so you do a cycle involving combustion products. And you put the data on. So combustion means you take these compounds and you burn them and they turn into the combustion products. So the arrows go that way. And this one on the right, that's easy because it tells us that when you burn 1 mole of that, which is what we've got, that's minus 1191. But the left-hand side is trickier. First of all, we have no number for epoxy ethane, because that's the point of the question. We've got to find it. So as we've done before, we call it X. And what about the water? Because you can't burn water, but of course the point is that water is a combustion product. If you feel slightly uncomfortable about that, you can see that if we wrote this explicitly as C2H4O, and this is C2H6O2, then the products of combustion, we've got 2 carbons, so would be 2 CO2s, and we've got 6 hydrogens, so that's 3 H2O. And you can see that that water is just one of these waters here, so it's being unchanged and going from there to there, and so it makes no contribution. It's just like when we had elements in the enthalpy of formation examples, where the elements made no contribution because they were unchanged from the elements down here to being in the equation at the top. And here we're saying this water on the left hand side is unchanged in forming the combustion products, so we just ignore it. Okay, so we don't need to do that. We can just keep this as combustion products, but because we know that water is a combustion product, we say, right, we just ignore that. So actually, all that happens on going from here to there is this burns with an enthalpy change that's X, and the water stays the same, so it makes no contribution. So that's our cycle, and then we can just summarise what that cycle tells us, which is that this reaction across the top, minus 115, is equal to, and then we need our 2-step pathway that corresponds to that. So this is what we're saying is our minus 115, and it's going to be equal to that plus that. Okay, so the first leg of the journey is exactly the same as this one, arrows going the same way, so the delta H is the same, it's just X, where X, remember we've defined, and we should have written this down, is the delta H of combustion of epoxy ethane. Okay, so that's our number that we're going to find at the end. But the second leg of the journey is the opposite of this one. So we're unburning the combustion products, if you like, to turn them back into ethane 1,2-diol. So it's the opposite of this, so the sign changes. So that's plus 1191 going up there. So now we can write down the sum of those 2 legs adds up to minus 115. So minus 115 is equal to X plus 1191. And therefore we can easily rearrange that. So subtracting 1191 from each side, we get minus 1191 minus 115 is equal to x, which works out as minus 1306 kilojoules per mole is our answer. Okay, so that's equal to minus 1306 kilojoules per mole. So you can see the same tricks that we used with the formation cycles we can use with the combustion cycles. You've just got to be careful, make sure you don't get them mixed up, make sure you get the arrows in the right direction. But the principles of what you do are all exactly the same. So the majority of Hess's Law calculations, enthalpy calculations that you'll get at A-level involve either enthalpies of formation or enthalpy changes of combustion. So all that stuff that we've been through, once you've nailed that down, that's going to deal with most of the questions where you have to do these cycles. Next year we'll use Hess's Law again, looking at some other issues to do with inorganic chemistry, forming ionic salts from their elements and dissolving those salts in water and breaking those processes down using Hess's Law. But again, those are quite standard things. Just occasionally though, they ask you to use Hess's Law to combine reactions which are just reactions, which aren't any of those sort of standard types of enthalpy change. So this is a case in point. So if you take sulfuric acid and you add sodium hydroxide to it, you know acid plus alkali goes to salt plus water. So this equation at the top is what you would expect the neutralization equation to be. There's your salt, sodium sulfate and water, and if you do that reaction you can measure delta H and it comes to minus 115 kilojoules per mole. However, if you only add 1 mole of sodium hydroxide, you can see you need 2 moles of sodium hydroxide for each mole of sulfuric acid. If you only add 1, then you get this reaction instead, where just one of the H pluses that sulfuric acid can release reacts, and the other one is still in place, so you get this compound. And if you measure delta H for that reaction, you find that it comes out to be minus 58 kilojoules per mole. So a question you might reasonably ask is, well, what if you then do the second leg and go take your NaHSO4, product of that reaction, and add the second NaOH to it to make Na2SO4 and another water. And the question you might ask is, well, what would delta H for that reaction be? And you can see that these reactions can be related using a Hess's Law cycle. Not anything to do with formation and combustion, but just combining the 3 reactions together. So let's see how that would work. So we're going to do that by first of all taking this top reaction, and that's going to be our reaction that goes across the top as the sort of overall reaction. So we've got sulfuric acid plus 2 NaOH goes to, let's put the number in there, Na2SO4 plus 2 waters, and that's minus 150. So what we can then do is say, right, well, what if we just do this reaction? Just react with 1 mole of sodium hydroxide. We can put that in, coming down here, and say, right, if we react sulfuric acid and we add 2 moles of sodium hydroxide, but only one of them is allowed to react, then we would get we would get NaHSO4. Okay, because we're now following this equation, we'd get NaHSO4 plus water, but of course we'd also have one of the sodium hydroxides left, right, because we added 2 moles of sodium hydroxide, but only one of them's reacted, so we have an NaOH left over there. So you can see that that change is actually exactly this reaction. because although it's complicated by the fact that we had two NaOHs there, one of them's still there at the end. So that NaOH didn't change, and therefore it doesn't contribute anything to the delta H. So if we leave that one out, the equation is exactly that one, and therefore this is minus 58. Now if we come up here, this reaction is actually the same as this one, because this reaction says that we have 1 mole of NaHSO4 and 1 mole of NaOH, so we've got those, but we've got a water as well. Is that a problem? Well, no, because that water's still there at the end. So again, you've got one water turning into two waters, so we cancel one of the waters out and say actually going up there you've just got NaHSO4 plus NaOH goes to Na2SO4 plus one water, which is that equation there. So again, it looks a bit weird, but when you realise that water isn't changing, it's just being carried through, so it makes no contribution to the enthalpy, so you edit it out and you realise that that reaction going up there is the one that we want. So that's delta H of reaction. So we could do this in various ways, but I mean, let's just stick to the method that we've used all the way through, which is to say, right, if this is our reaction across the top, we can break it down into two legs like that. First leg is the same as that one, so that's minus 58. Second leg is the same as this one, so that's let's call that x. Okay, delta H of reaction is x, so we'll call that x. So actually they're both going in the right direction this time, so we don't have any sign changing to do. So we can just make the statement that minus 115 is equal to minus 58 plus x. Okay, because it's minus 58 plus x going there. And therefore we can rearrange that, just add 58 to each side, and we get minus 57 is equal to x. Okay, so that's delta H for this reaction. Okay, so for this reaction here, because that's in effect what's happening in this third leg, that NaHSO4 is being converted into Na2SO4 by reaction with sodium hydroxide, the equation just looks slightly different because of this extra water that's being carried across, but it's not reacting, so it doesn't make any difference to the delta H. So delta H of reaction is equal to minus 57 kilojoules per mole. Now those kind of enthalpy cycles take a bit more thinking about, because it's not a sort of standard pattern that you're following. But the good news is that they don't come up very often, and when they do, they generally give you help. So they'll generally draw the cycle for you, or at least the outline of it, and just ask you to fill in the details. So it's not as frightening as it appears. But just be aware that although we're focusing mainly on enthalpy changes of combustion and formation in these examples, that you do sometimes get other examples like this. But underlying it all is exactly the same logic.